Hello, this is Mrs. Butcher here, and this video is over exponential functions. And today we're just going to be graphing the parent functions. An exponential function is any function that you have where you have y equals, and then you have some number, b, raised to the x power. So in the last chapter we did a bunch of things with squaring and a few other powers where the power was a number and the variable was the base. But now we have the base as a number and the exponent is the variable. And this only works if b is greater than 0 but not equal to 1. Because if b is less than 0, then we're raising a negative number to powers, and it won't work right. And if b is 1, well, 1 to anything is 1, so that won't work either. If b is greater than 1, you will have exponential growth. So your graph will get exponentially larger as x increases. The higher the power, the bigger the y value, obviously. Now, if b is less than 1, you're going to have exponential decay. As x increases, your y value is actually going to get smaller and smaller. Because when you raise a fraction to an exponent, 1/2 squared becomes 1/4. It gets smaller. And the higher you raise the power, the smaller it gets. And yeah, that's my son Adam singing in the background, so I hope you enjoy the entertainment. Now your exponential growth parent function is y equals any number b raised to the x power. Oh, look at text. And when b is greater than 0, greater than 1, we have exponential growth. Now let's imagine the graph for this. Let's start with 0. Anything raised to the 0 power is 1. So for any of these, if we made a table, when x is 0, if we raised it to the 0 power, we would get 1. And then if x was 1, b to the 1 power is always b, whatever b is. It could be 2, 3, 4, it doesn't matter. So we'll just put this and we'll just call this b. So that point right there is 1, b. And that point right there is 0, 1. And then, if we think about if I were to make x -1, then if I raise something to the -1 power, that's the reciprocal of it. So 1 over b. And so that's a fraction. And so the higher that x gets, I'm going to square b. It's going to get bigger. I'm going to cube b. I'm going to 4th power b. It's going to grow really quickly. Whereas here, I'm going to do -1 power is half of it. -2 power would be 1 over the square of it. And it just gets smaller and smaller and smaller. However, it will never actually equal 0. So it approaches this imaginary line that we put right here. And I'm dashing it in, and that is called an asymptote. And that's a very important word, so I'll define it on the next page. That's the asymptote. In this particular one, it's an imaginary line at y equals 0. Okay, so an asymptote, that would be a very important vocabulary word for you, is an imaginary line that a graph approaches but never touches. And you can think of it as if, like a half-life, if you've learned about that in science, or like halving anything. If I were to walk half the distance from A to B, if I were to walk halfway, and then I were to walk half of that, and then I were to walk half of that, and then I were to walk half of that, and half of that, and if I went half my distance every time, I would never actually reach the destination. You would get infinitely closer and closer and closer, but you would never actually touch it. And that's what an asymptote is. Your graph is getting closer and closer and closer, but it's just going to approach it and then skim right along it, but will never actually touch it. Now our exponential decay parent function is still y equals b to the x power. Only when it's decay, b is anywhere between 0 and 1. So any fraction or decimal that's between 0 and 1, not including 0, not including 1. And when you have exponential decay, your graph's going to look something like this. Alright, just like before, if x is 0, and I raise anything to the 0 power, y is 1. So I have this point right here at 0, 1. Now, if x is 1, and I raise b to the first power, then y is going to be b. But since b is between 0 and 1, it's going to be down here. So that point is at 1b. Same as before, it's just that b is less than 1 this time. And then if I were to go higher powers, like 1/2 squared is 1/4, and 1/2 to the third power would be 1/8, and it just gets smaller and smaller and smaller. And when you go the other direction, if I had -1, y would be 1 over b. But since b is a fraction or decimal, it actually gets bigger. So it goes up. So it's just the opposite of the exponential growth. And just like before, we have an asymptote right here. It's approaching it. Sorry, I didn't mean to make it go across the graph. It's actually, the graph is approaching this imaginary line. And it's at y equals 0. So anytime we draw our exponential growth or decay graphs, I want you always to draw in your asymptote as a dashed line. The other thing that we need to talk about with these is domain and range, because we always talk about domain and range. The domain for these, x is going infinitely to the left and infinitely to the right, so that would be -infinity to +infinity. But our range starts wherever the asymptote is, in this case 0, and it doesn't touch it, so we put a soft bracket on it. And then since this one's going up to +infinity, it's 0 to infinity. So for our first example, we're going to graph y equals 3 to the x power. And to do this, we're just going to make a table. Alright, so here we have y equals 3 to the x power, and all of these exponential parent functions will have our asymptotes at y equals 0, so draw in a dashed line with your asymptote. And then let's just start, we'll always start with x equals 0 because that's a nice easy place to start. So if x is 0, 3 to the 0 power is 1, 0, 1, because they all have a point at 0, 1. Then if x is 1, 3 to the 1 power is 3. So we have a point at 1, 3. And see that 3 is our b value for this example. So 1, 3. If x was 2, we'd say y is 3 to the second, and 3 squared is 9. 9. Whoops. 3 squared is 9. So we have a point at 2, 9. And then if x was 3, 3 to the third is 27, and that's way on up there. So it grows really, really quickly. Now in the other direction, if x is -1, you have to think about what is 3 to the -1 power. Remember, a negative exponent means reciprocal. So that's 1 over 3 to the +1, or 1/3. So when x is -1, y is 1/3. Then if x was -2, 3 to the -2, that's 1 over 3 squared. So 1/9. And it just gets smaller and smaller and smaller and smaller, 1/27th and so on, and then approaches that asymptote. Now our domain for this function, for this graph, is going to be -infinity to +infinity, all x's. I'm sure my kids are entertaining you guys today. My range, the lowest y can be is that asymptote at 0, but it's not actually going to touch it, so go with a soft bracket on 0, and then it is going infinitely upward, so 0 to infinity. And this graph is exponential growth. You can tell this because your b value is greater than 1, and you can tell it by looking at the graph because the graph is from left to right going up, increasing. It's exponential growth. Alright, so let's do one more example. Okay, so for this one we're going to graph y equals 1/2 all raised to the x power. So this time our b value is 1/2, which is between 0 and 1. So this should be an exponential decay graph. Alright, we're going to make a table. We'll start with x is 0. Anything raised to the 0 power is always 1. If you don't believe me, you can punch it into your calculator and see. So 1/2 raised to the 0 power is 1. We have a point at 0, 1. And then when x is 1, 1/2 to the 1 power is 1/2. So that point's going to be there. When x is 2, 1/2 squared is 1/4. So that's there. 1/2 cubed would be 1/8, and then 1/16, and so on. Getting smaller and smaller, but not actually reaching 0. If x is -1, this is where it gets tricky. We have 1/2 to the -1 power. -1 means reciprocal, so that's 2 over 1. And 2 over 1 just equals 2. So we have a point at -1, 2. And then if x is -2, 1/2 to the -2 power means the reciprocal to the, 2 over 1 to the second power. So 2 squared is 4. -2, 4. If x was -3, then y is going to be 1/2 to the -3rd power, which is the reciprocal. 2 over 1 to the 3rd, that's 8. So really, it's just the exponential growth function in opposite, isn't it? So we're going to have -3 and 8. And then 2 to the 4th is 16, and so on, and it just gets higher and higher, faster and faster. Except that that is actually coming down from left to right, so we call it exponential decay. And I want you to draw in your asymptote, just like always. That is a dashed line right here at y equals 0. And then our domain and range, the domain here, all real numbers. X could be anything. Our range starts at 0, goes on up to infinity. So those are the parent functions of growth and decay. Now, the b value could be anything. So when we have our parent functions, we don't actually have just one for each. We just have anything raised to the x power, where x is either, where b is either any number greater than 1 or any number between 0 and 1. But these are just a couple of examples of our apparent functions of exponential growth and decay. And tomorrow we'll talk about the more complicated ones where we add and subtract and shift and all that. But today I just want you guys to get a good idea and a good feel for what these standard exponential growth and decay graphs look like. So when you do your assignment in class tomorrow, that's what we're going to work on. All right, hold on just a second. Okay, whoa, that was weird. So I guess like the last few minutes of what I did didn't actually record what I wrote, but if you can see it here, that's what I meant. So please go in your notes and adjust and make it look right, and I'm sorry about that. But since I'm running out of time, I'm just going to have to leave it like this and fix the video later. But anyway, I guess that's it really for tonight. I hope you guys have a good night, and that's about it. So yeah, good night.